Hello and welcome back to Calculus 3. So today's section on a dot product is actually lecture on generalized multiplication. You are used to the one-dimensional version of the dot product, which is your multiplication tables. So when you say 3 times 5, what you are actually multiplying are two one-dimensional vectors, and you're getting 15. So we can write this in a vector notation. We never do it, but we can. We can write it as vector 3 times vector 5, which gives us 15. The outcome at the end is the area of these two input vectors, and we know that we have 5 vectors I stacked one j or whatever, and then 3 this way. So when you take a look at this size over here, we have a rectangle of size 15. So there are 15 squares in this thing. So now, what is the dot product? Well, the dot product is going to be multiplication of vectors. But now, since vectors can be in any dimension, this is going to be the multidimensional product. So if I have, and we can leave this as a formula for 2D case, if I have vector u dotted with vector v, I have u1, u2 dotted with vectors v1 and v2, and that's going to be u1 v1 plus u2 v2. So that's the formula that we are going to use to compute the dot product. Note that the answer is scalar. Again, it's not a vector. So let's put the example so we can actually see all of that right away. If I have 2, 3, and let's say negative 4 and 7, whatever. We're going to say 2 times negative 4 plus 3 times 7, which will give us negative 8 plus 21, for a total of 13. So when you multiply two vectors, the answer that we get is a scalar. As I said earlier, 3 times 5 is 15. Now if you multiply these two-dimensional vectors, you will get 13. Now, what I can do is I can put this in any dimension I want. So I can go with a 3D, 4D, 5D, any dimension that we think of. So u dot v as thru-dimensional vectors, so u1, u2, u3, dotted with v1, v2, v3, will give us u1 v1 plus u2 v2 plus u3 v3, again a number. So dot product works in any dimension. and the product is always a scalar quantity. So as a quick exercise, you guys multiply 2, 0, negative 3 with 6, 1, and negative 2. So we have 2 times 6 plus 0 times 1 plus negative 3 times negative 2, which is 12 plus 6, which is 18. You all cool? 18? Awesome. Now, let's talk about definition and use for the dot product. So, dot product definition. The dot product between two vectors in any dimension, so I'll put here any dimension. So the dot product is defined as the product of magnitudes times the cosine of the angle between two vectors. The previous formula is the way to compute dot product. This formula is its purpose in the galaxy and beyond. So now, if I have two vectors u and v, I will have angle between them, angle theta, which means that I can flip this formula and solve it for theta equals inverse cosine of the dot product divided by the magnitudes. So now this form calculates the angle between two vectors. What should be the angle between vectors I and j? Prove it. So prove that I and j vectors are 90 degrees. What is the definition for vector I? 1, 0. Oh, you want a 3D? Sure. And then J? Okay.
Ponašaj se normalno. Jesi čuo? Dođi ga.
So we know that these are unit vectors, hence those little hats. So the magnitudes are 1. And we have theta equals cosine inverse of the dot product, which will give us 0, divided by 1 times 1. So we have a cosine inverse of 0, which is pi over 2 radians. So theta equals pi over 2 radians, which is 90 degrees. So this is a proof. Now we're going to write a theorem which is used a lot as we go on through this chapter. And it says two vectors u and v are orthogonal if the dot product is 0. If and only if u dot v equals 0. So this is the theorem that goes back and forth, right? Works both ways. If you know that the dot product is 0, then the vectors are orthogonal. Or if you know that the vectors are orthogonal, the dot product will be 0. So it works both ways. Again, works in any dimension as well. So we quickly look for 0 in the dot product. If the dot product is 0, then we have orthogonal vectors. Obviously, none of the vectors is supposed to be 0. Remember what a 0 vector is. It's just a dot at the origin. Vector has no direction, vector has no magnitude. It's just a 0 vector in whatever space you are observing it. So if you have a R3 space, your throw-dimensional 0 vector is just going to be the dot at the origin. Now, because there's no magnitude to the vector, it cannot be perpendicular to anything, which makes sense because its magnitude is 0, and you can't have 0 in the denominator of our formula, right? So it all makes sense and everything fits greatly. You just have whatever vectors you have, they have to be the same dimension, and then you are not allowed to have 0 vectors because that will create 0 in the denominator for the calculation over here. All right, let's see if there is anything else that it's cool. Properties of dot product. Number 1, dot product is commutative. So this is one of the proofs. If you want the honors option, you can do it with 2D vectors u1, u2, v1, v2. Then we have associative property. And finally, distributive property. If you want to prove any of these, you can just use, 2 by maybe 2D case, 3D case. There are more general proofs, obviously. If you're a math major, you should be considering it. Orthogonal projection. This is important because physics. All right? We want to find the component of the force which does the work. We touched briefly on physics in these examples, and especially in this example with a crate, I talked about you making it worse for yourselves when you are pushing an object and you lean on it at the angle, right? We talked about it because looking at the diagram, right, if I lean onto the object, this force with which I am pushing gets decomposed into a vertical force, which is the one that is pushing the object down, making it heavier. Heavier object, more normal force, more friction, and the friction is opposing my push, right? Now, what is the force which pushes? The force which pushes is the force of the push in the x direction, which is when you drop the normal down, just this component which pushes straight forward. So that component there can be computed by what we now going to look at and call orthogonal projection. So we are going to project the vector which does the work and only take the component which actually produces the work. The other component is making everything worse. So if you are considering the situation with a crate, and you have the vector f P, F of a push, you know that the only component which would do the work is the horizontal component parallel to the floor. If you are to shine a light onto this vector, it will put a shadow here, and this would be your force of the push in the x direction, which is the one that does the work. That force times the distance is going to give you the work. So when you look at it, this force Px is actually projection of vector Fp. These are all vectors, right? Onto the floor, because that's parallel to the floor, and that's the component that does the work. So now, that was explanation of where you find this in physics and so on. One of the easiest examples, obviously. But in mathematics, we are free to have this oriented in any way we want in space. So, in general, when we are explaining this in math terms, we have our vector u and our vector v, and we want to compute the projection of vector u onto vector v. And again, the way this is done is we are going to shine the light onto vector u, and that will give me vector v projection of u onto v. So the red one over here is the projection of vector u onto vector v. Now, this projection is computed by the dot product u dot v divided by v dot v, and all of that times vector v. This is the formula that you guys will learn. Now, if you are trying to reason with this, these two in the denominator, they could have, we don't need it in a formula, but we could put the magnitudes in. And if you think about this, you would see that over here you essentially have V over absolute V. Now, what is that? Unit vector. Unit vector. So this is the unit vector in a direction of V. Please note that the red vector over there is in the direction of vector V. So you have this component in there that gives the direction, and the other three give us the scaled magnitude of the scaled magnitude. Now, the full derivation for this is in the book, and again, it is something that honors students should know. So everyone is equally responsible for the formula, obviously, to be able to compute the projection. But if you're signing up for honors option, you have to make sure also that you are able to pinpoint these things, so where the magnitude comes from, where the direction comes from, and so on, because obviously this new vector, the projection vector, is not vector v, because it has different magnitude, and it's not vector u, because it has direction. It's a combination of the two, so that you are projecting vector u onto vector v. Common sense is that the projection vector and vector v will have the same direction, because projection vector sits on vector v. And obviously projection is also not commutative. So if I want to flip this around, projection of vector v onto u, so if you want the other way around, it's going to be u dot v and then u dot u dot u. If you are projecting v onto u. So how about you guys compute projection? So u is given as 1 and 3, and v is given as -2 and 6. And compute both of these, projection u onto v and v onto u.
Supposed to be a vector.
Yes?
Isn't the thing outside a dot though? Isn't that a scalar? Yeah.
But this is a scalar, right?
Yeah, but then the u, that isn't that a dot?
The dot is the multiplication.
Oh, sorry.
So multiplication, if you have two vectors, it's going to be dot product and it's a scalar. But if you're multiplying constant by the vector, you are just scaling the vector u. So over here, this is the dot product, this is the dot product, and this is the product.
It's a scalar times one.
So this will be scalar, right? And the reason why I'm asking you to compute both is to see that they're not the same. You have to be careful which vector you are projecting onto which. So projection u onto v and v onto u is not the same. So do we all have negative 4/5 and 12/5 for the first one? Yay. Did something right. How about the other one? Projection of vector V onto U. What happened?
What part are you asking?
The other projection.
I got 8/5 and 24/5.
8/5 and 24/5. Is anyone confirming this? I'm just going to say, okay, fine, let me move on. Good job. So as you can see, they're not the same. So now, in physics, work is defined as the force times the distance, which we know we can write as force, magnitude of the force times distance of the force times the cosine of the angle in between them. So as you push that crate at the angle, you can compute the force, the work. So as we push at an angle of, let's say, 30 degrees with a force of 50 newtons, and let's say we push the whole thing 3 meters. So I have my distance vector to be 3, 0. Now you can also put negative 3, 0 because we are pushing to the left, but it doesn't matter. And we have our force vector that is 50 newtons. Now that's magnitude. So force is 50 newtons. Now I will use the magnitude portion. So work is equal to magnitude of the force times the distance times the angle between these two. So I have the 50 Newton push times 3 meters in distance at times the cosine of 30 degrees. This is 150 times root 3 over 2. So work is 75 root 3. It's about 220 joules of work. Now, if you want to use the other formula, right, the dot product to come up with work, you would actually have to combine the given specs on a vector to get a vector. And you can use the I and j components and all of that to put the vector together, but it's just, much longer to solve the problem that way. And the same story of the incline, which I covered the last time, is back in this lesson again, right? Where your block on the incline will have 4 forces acting on it. 3 forces will be offset by the angle, and the weight would be the only force that goes straight down. And I taught you a trick that by rotating the system, you get to put 3 forces to be in line with the coordinate system, and only the weight in that case would be rotated for the angle theta. So rotating coordinate systems is very beneficial to solve these problems. And that's the dot product. I hope you're not disappointed. The dot product is going to be used to find the angle between 2 vectors. And those vectors could be in any dimensional space. Maybe that would be also another good thing to mention. So if I have 2 vectors, this vector now is in 3-dimensional space. And this vector is in 3-dimensional space. As soon as I put these 2 vectors so their initial points touch, you see that these 2, no matter which way you put them, doesn't matter. Note that no matter in which position these 2 vectors are, you can always take and put the plane through these vectors. You can always define a plane. So if these vectors are this way, here is the plane that is defined by those 2 vectors. If you change the configuration of the 2 vectors like that, you can still put a plane through those 2 vectors. No matter which way you orient these 2 vectors in 3D space, they will always give you a plane. And the angle theta between these 2 vectors will be in that plane. So technically, you can have a 7-dimensional space with 7-dimensional vectors. You have the 2 vectors, and they will always have a plane to go through it, and that angle between the vectors will always be calculated by the dot product regardless which dimension you're in, which is really cool. Our next lecture on cross product doesn't do that. So we'll have to be we have to be more careful. And the homework goes again with 5,000 problems to find. Just want to see if there are any constant force, orthogonal projections. Yes, this is one of the cheap homework assignments. All right, so that's that.